Swayam Prabha. Digital India. Educated India.
Good morning, students, and welcome to another session of our series of video lectures on Introduction to Aerodynamics. In the previous classes, we have covered broadly, we talked about the textbooks that are required for this, that are, I would recommend you guys to go through it. I said that primarily these were the two books that you should, go through from end to end, and otherwise the remaining of the books, it is good to have so that you can glance through it as and when you need. I also just put up the picture of the deck of these textbooks so that at least you have a visual appreciation of the kind of books that I am recommending you to go through. Then I also told you that there is this series of very important, I must say, very important series of video lectures, or rather not video lectures, these are more like video demonstrations of some of the fundamental fluid mechanical behaviors. And if you are really intending to pursue on a long-term career in fluid mechanics, aerodynamics, high-speed flows, etc., it is absolutely necessary that you go through this. So if you see here, there are all these series of topics on which the stalwarts from the era, like the 60s, 70s, and I think early 80s, they have showed experiments of fundamental concepts like what is viscosity, demonstrated what is an Eulerian frame, what is a Lagrangian frame, the details of boundary layer theory. For example, when you read a textbook, when you try to interpret things from the text and the images, it is not always easy to understand because fluid behavior is complex. But when you see it visually, a lot of things that you may not be able to appreciate by reading a book or looking at an image, you will actually appreciate when you watch these videos. And these videos, as I repeat, that these are made by some of the stalwarts in those areas. So it is absolutely necessary that you should go through this series of topics on which they have very good videos. They are available on YouTube. I think you can also go to this page and click on these links. In fact, today, for example, our discussion will be primarily on the phenomena of drag. So drag is one of the four important forces that act on an aircraft during its flight. As you remember from our introductory lectures, you have an aircraft has a force which is the weight of the aircraft that acts vertically downwards. Of course, any physical object in the gravitational field of the planet would have a gravitational pull, which essentially translates into the weight of the object. Of course, you know that at various altitudes, your weight, because the value of g, small g, would vary with altitude. So the weight might change slightly, but again, in the range of flight altitude variations, we sometimes just can take weight as something that is the g at sea level. But if you want to be precise, you should calculate g at the altitude and then take the force, the weight that is acting on the vehicle. But apart from that weight, which comes from gravity, you have these the force of lift and drag, and of course you need thrust to somehow fight against these forces, essentially your drag and your weight. So you need some way in which you have to fight against these two forces. So drag is a force that prevents the motion of the vehicle in its intended direction. I think all of you have experienced drag in one form or another. For example, if you have ever stuck your hand out of a moving vehicle, and if you have felt the wind blowing past your hand, you have realized that although your hand is moving forward, the flow of air around your hand is trying to push it backwards. Now think of an aircraft that is moving at 900 kilometers per hour to 3,500 kilometers per hour. If you think of the SR-71 Blackbird, it's flying at it can fly at speeds as high as 3,000, 3,500 kilometers per hour. So think of the amount of drag some of these vehicles can experience as they fly through air. Now, you understand that the drag on an entire aircraft, so we are really interested in drag on the entire vehicle, weight of the entire vehicle, lift force generated by the entire vehicle, and the thrust generated by the entire vehicle. Now, you understand that the thrust generated by the vehicle is essentially thrust generated by the engine that is mounted on the vehicle. You will, in advanced courses, you will see that when we talk about hypersonic vehicles, we don't talk about like engines mounted on the airframe. You will see that there we talk about engines integrated with the airframe, because what happens is it is a very high speed vehicle. So right now, in this introduction to aerodynamics, our focus will be primarily on the subsonic aircrafts, high subsonic aircrafts, supersonic aircraft, and a little bit of 1 or 2 lectures on what is hypersonic aerodynamics. But if you are talking about very high speed vehicles operating in the hypersonic range, there is this engine called the scramjet engine, which is not like a gas turbine engine that you mount on pods on the wing, because the amount of capture of air that you have to do is enormous. So these engines, the scramjet engine in hypersonic vehicles, flight vehicles, is integrated to the entire body of the aircraft. So you will not see engines on the hypersonic vehicle that are mounted on a pod or nacelle kind of arrangement. The entire undersurface of the vehicle actually acts like the engine. Okay, so the engine is totally integrated on the undersurface of this vehicle. However, for the kind of aircraft that we are more used to seeing around us, if you think of the Indigo, SpiceJet, Airbus, A320 kind of aircraft, you see that on the wings you have the two, 1 or 2 engines on each side. Now, these engines provide the thrust for the aircraft. In terms of the lift and drag, so we will come to that. So lift and drag are generated when there is relative motion between the vehicle and the surrounding air. We are interested in the drag part at this point. So in this lecture and in the sequence of lectures following this lecture, we will focus on the drag component of force that acts on an aircraft, and we will see that the drag on the entire aircraft is essentially a summation of some sort of drag on the individual components of the aircraft with some interaction between them, with a factor of that interaction between them taken into account. So what I mean by this is, like the drag or the force that is preventing the aircraft or trying to prevent the aircraft from moving forward is composed of drag on the fuselage, drag on the wing, drag on the engines mounted on the wings, drag on the nacelles that connect the engines with the wings, drag on the horizontal stabilizer, vertical stabilizer. So drag on everything adds up to the drag on the entire vehicle. However, keep this in mind that you cannot just find the drag on the fuselage by itself, drag on the wing by itself, and add them together to get the drag on the entire aircraft, because when all these things are fitted to one another, the flow around the fuselage is affected by flow around the wing. Flow around the wing gets affected by flow through the engine. So all these components affect the flow around each other. So the drag on the entire aircraft is not exactly the drag on individual components measured separately and added together. Okay, so there is some kind of interaction going on. So although I am saying that the drag on the entire aircraft is a combination of drag on these individual components, by now from our lecture on the parts of an aircraft, you know that aircraft has all these fuselage, the main wing, the horizontal stabilizer, vertical stabilizer, the engines and the engine mounts or the nacelles through which they are connected to the wing. So the drag on the entire aircraft is a combination of drags on all these things, taking into account the interaction of these components on each other, or the influence of these components on each other as far as aerodynamics is concerned. The movement of air around each of these components is affected by the activity or by the presence of this other component. Okay, so you have to keep in mind that although we say the component contribution has to be taken into account, but the interactions also have to be taken into account. Now, you will see that I have several lectures on the fluid dynamics of drag on aircraft. Now, some of you might be wondering that in an introductory course in aerodynamics, why am I not starting with the traditional approach of first deriving the governing equations. You will see that we have the continuity equation, momentum equation, energy equation. These equations can be derived in starting from a differential element or from a like a control volume kind of approach. One will lead to differential forms of the governing equations, the other will lead to integral forms of the governing equations. And of course, these governing equations, either in integral or differential form, can be shown to be equivalent to each other, of course, because they represent the same physics. After that, in a typical course, people will talk about, or instructors would talk about, concepts like what is vorticity, what is deformation, what is rotation of a fluid. Because remember, your fluid and a solid object, when a fluid is, when a package of parcel of fluid is moving through a flow field, it deforms. Under any kind of shear force, it will continuously deform. It will rotate. It will, of course, translation and all those things are there. But if you look at the object, the rotation of a fluid element is very different from the rotation of a solid element. Okay, so in a course in fluid mechanics or introductory aerodynamics, some instructors like to discuss all these things a priori, then talk about what is circulation, what is vorticity, how they are connected, Kelvin's theorem, what Helmholtz vortex theorems. And once they are done with all these building blocks, they get into these applied problems. What the drag on an aircraft, lift on an aircraft, etc. But I have seen that it serves better to start with a physical problem. So here we will start with the drag on the aircraft, and while we are discussing this drag on the aircraft, we will touch upon the building blocks or the fundamental concepts that are required to understand this physical process. Okay, so instead of going through the fundamental aspects themselves in isolation and then starting a physical problem and trying to find the use of those things on this problem, we will try to bring the fundamental building blocks as and when they are required to understand these core concepts. And I have a feeling that if you understand drag completely, I mean, it is not always easy to understand these things completely, because it's a natural process. A lot of things are modeled, so these are the best to what we understand. But nonetheless, if you understand drag, or in order to understand drag properly, you will need to understand all the elements of basic fluid mechanics. So I think this topic will give you an opportunity to understand the utility of those core concepts. So let me now, okay, so this I have shown. Okay, so today, as I said, we will talk about the physics of drag. And here you see I have talked about boundary layer basics, skin friction drag, flow separation drag, etc. So we will see that the drag on the aircraft, which is composed of drag on the individual components with some interactions taken into account, can be broken down again. So for a given component, the drag will be a summation of various kinds of drag. So drag on an aircraft is equal to the summation of drag on its components with the interactions between them. Now, if you zoom into one component, say we are zooming onto the finite wing that are stretching from the root chord to the tip chord away from the axis of the fuselage, and we are interested in finding the drag on these wings. We will see that there are various sources of drag that are acting on the wing, and that will be our the structure of these next few lectures. So we will try to figure out what are the sources of drag on a given aircraft component, and we will focus primarily on the wing. And you will see there are good reasons for that. If you understand the drag on the wing, then it is not very difficult to extrapolate it into drag on fuselage, drag on horizontal stabilizer, vertical stabilizer, engine external mounts and the nacelles, etc. So if you understand drag on this one primary component, because wing is a primary component, and you will see that a big chunk of drag actually comes from lift. So this is a little bit of like a surprise to many, that lift is a force that is directed perpendicular to drag. If you remember that we have shown this image So, if you see, lift is directed in this direction, whereas drag is directed in this direction. So, lift is, I said, a force that is resolved normal to the relative wind. So, this is the relative wind direction, and drag is the force. So, what is that force? So, when air is moving around the vehicle, or when we talk about, say, the drag on the wing, so you have to say that, it's not just the drag. You have to say whether you're talking about the drag on the entire aircraft or you're talking about the drag on the wing. So, nonetheless, drag force is, so when air is moving over the wing or the vehicle, there is a resultant force. Now, you resolve the resultant force along the relative wind, that is the drag. So, you see that if this is your relative wind, just a second. So, since this is your relative wind direction, and as the air flows over this vehicle, it creates some reaction force. So, use some reaction force. So, you see that as air is moving over the wings of the vehicle, it creates a resultant force, and we will get into the details of it very soon. Now, this resultant force R can be resolved along the direction of the relative wind. So, this direction is same as this direction. So, if you resolve this resultant force R along the relative wind direction, you get the drag. So, you see this is the drag. On the other hand, if you take the component of this resultant force normal to the relative wind direction, you get the lift. Okay, so, this is your lift and this is your drag. You will see that this drag is composed of, so drag on the wing, as I said, if you understand drag on the wing, it is not difficult to find drag on other components. So, drag on the wing is composed of, we will see something called skin friction drag, so when air is flowing over the wing, it is creating a resultant force R. I said you can decompose R into a direction normal to the relative wind, you get the lift. You decompose it along the relative wind direction, you get the drag. Now, the question is, what is the source of this drag? What I am writing down are the different sources where this drag force on the wing comes from. One of them is the skin friction drag, and this is due to the viscous nature of fluid flow near an object, skin friction drag. Then we have something called pressure drag. You will see that it is, if you look up a textbook, invariably in most cases they will say pressure drag due to flow separation. Okay, so drag is composed of skin friction drag due to viscous effects in the neighborhood of the wing. So, drag on the wing, let's just, okay, this should be applicable everywhere. So, let's keep it drag for the time being, but we are discussing drag on the wing, or rather we will discuss drag on the wing. So, drag is composed of skin friction drag, which is really due to viscous phenomena, pressure drag due to flow separation. Now, this is interesting. What is flow separation? First of all, what is pressure drag, and then what is that qualifier due to flow separation? In fact, in supersonic flow fields, pressure drag can arise without flow separation. If you resolve the net force arising from the pressure distribution along the relative wind direction, you might find some drag as well. Here also you will find some drag, but it will be negligible. So, when there is no flow separation, the contribution to drag due to pressure distribution will be very small. Okay, we will see that. In fact, in inviscid incompressible flow fields, there is no drag, and that was the famous D'Alembert's paradox. That is, how can you have a flow field? So, you put an object in a flow field, And some mathematical analysis of the 17th century, 18th century, these mathematicians and theoreticians were seeing that if you model fluid flow like an incompressible inviscid flow, then there is no drag on the body, on the 2D cylinder or whatever you have immersed in the fluid. However, practicing engineers saw that of course when you put something in a flow of water or something, you have tremendous drag. So this we will come at, this discussion we will have at some point. But at this point, just keep in mind that skin friction drag is due to viscous effects near the wing or near the body. Pressure drag due to flow separation. Now flow separation is also something that has to do with viscous drag and boundary layer. But nonetheless, we will see that when you have flow separation, then the pressure distribution on the object or the body of fuselage, wing or vertical tail, etc., becomes skewed. So pressure distribution becomes such that there is a large amount of resultant or force in the direction of drag. After that, we will see that there is something called wave drag, and this will primarily show up at high subsonic Mach numbers. Of course, in supersonic flow fields, wave drag is there, but if you talk about subsonic aircrafts flying at Mach numbers less than 1, generally you won't have these shock waves. But if you come close to Mach 1, there is something called the critical Mach number and the drag divergence Mach number. We will talk about these things at some point while we discuss the drag. We will see that when a vehicle reaches something called the critical Mach number, so the free stream Mach number is still subsonic, say around 0.8, but since the flow accelerates and decelerates on different parts of the aircraft, it might so happen that you might reach a point where the acceleration or local acceleration is large enough to give you a local Mach number of 1. So that is, so the free stream Mach number that gives you a local Mach number of 1 for the first time. So as you are increasing the free stream Mach number, there are portions on the aircraft wing whose Mach number is larger than the Mach number of the free stream. Mach number is defined as m is equal to u by a, where u is the flow speed or the flow speed or the speed of the vehicle with respect to the flow. So you can either consider the vehicle at rest and the flow going past the vehicle, or you can think of the flow being at rest and the vehicle is moving through the medium. So in u is the relative velocity between the body and the medium, and a is the speed of sound. Now why we divide these by the speed of sound, and instead of talking about the relative speed, wind speed or the flow speed, we talk about this Mach number. It is essentially like there are different kinds of velocities that will be of interest to you. For example, for the ground speed of an aircraft will be of interest to the aircraft operator. That is, the distance from Calcutta to Bangalore is so and so, and the speed of the aircraft is so and so kilometers per hour with respect to the ground. So an aircraft operator would like to know this so that it knows what will be the time of arrival, given a time of departure. However, when it comes to fluid mechanics, the flow behaves in different ways at different Mach numbers. So that is why as aerodynamicists, instead of talking about say ground speed or true air speed, we talk about in terms of Mach number, because we will see that a lot of aerodynamic phenomena show up or do not show up just based on the Mach number at which you are operating. So from the aerodynamics or the fluid mechanics point of view, Mach number becomes important. Okay, so Mach number is given by the speed of the vehicle or the speed of the flow, or the relative speed of between the vehicle and the flow, divided by the local speed of sound. Now why are we so concerned about the local speed of sound? Why sound? Now this is not like your sound of music or noise that we are talking about. Sound is nothing but mechanical disturbances in air. So we are saying the ratio between the speed of the object and the speed at which mechanical disturbances created by the object move away from the object it has some important connotations. So, the ratio between the speed of the object in the medium divided by the speed at which mechanical disturbances created by the object while it is moving through the medium. So, the ratio between these two, the speed at which the object is moving and the speed at which the mechanical disturbances created due to the motion of the object are moving. So, this ratio we will see has very important connotations in the entire of aerodynamics. So, this is one of the something known as the similarity parameters. So, Mach number m defined as u by a, where u is the flow speed and a is the speed of sound, is a very important similarity parameter. For example, suppose you are trying to run a wind tunnel experiment on a small model aircraft and you are trying to figure out what is happening with its real scale, full scale counterpart flying at 30,000 feet above the ground. Now, at what condition are you going to run the experiment in the wind tunnel? At what conditions running the wind tunnel and getting the data will really be reflective of what is happening at 30,000 feet given some temperature and some velocity, etc. We will see that you have to match two similarity parameters. One is the Mach number and the other is something known as the Reynolds number. We will see these things. I am just talking, we like to introduce these things several times so that repetition helps you understand some of these concepts. So, we will have some elaborate discussion on what is Mach number, what is Reynolds number, but at this point just for so that we can continue with the discussion and have some sense of these things. So, your wave drag is something that shows up when the vehicle speed is such that you are starting to have shock waves on some portions of the wing, for example. Okay, when you have the shock waves, it can be that flow regime of a subsonic aircraft where it has crossed its critical Mach number, entering something called the drag divergence Mach number. So, now you know what is a Mach number. You know what is critical Mach number. Critical Mach number is the Mach number at which free stream Mach number, where because flow has accelerated or decelerated here and there. So, in the regions where flow is accelerating, you can have a velocity which is larger than the free stream velocity. So, you can have a Mach number which is larger than the free stream Mach number. So, at some point this local Mach number can reach 1 even when your vehicle is flying at a subsonic Mach number less than 1 Mach number. Typically, it has been seen that when your vehicle is flying at something around Mach say 0.8, some portions of your wing might actually be having Mach numbers of 1.1, 1.2, even more than that. So, it is not always that supersonic flight or supersonic considerations or shock wave considerations come into play only for supersonic free stream velocities. You can also have subsonic free stream velocity close enough to the Mach number 1 where flow has accelerated. We will see where flow accelerates, why flow accelerates. You will see that on the top surface of the aircraft, flow speed actually is on the average lot more than the flow speed on the bottom surface. And there are many theories, there are popular theories which are incorrect. We will see some of the more physically sound explanations of why that higher speed on the top, lower speed on the bottom. What is the implication of the higher speed on the top, lower speed on the bottom? You will see that that is the whole basis of lift, the higher speed on the top surface of the wing and lower speed on the bottom surface of the wing. But the question is why that distribution of speed happens. And once the distribution of speed happens, of course, you can use something like Bernoulli's theorem. So, we will talk about what is Bernoulli's theorem, go through the derivation of Bernoulli's theorem. The derivation will be important because it will show you two things. First of all, when you just read about Bernoulli's theorem and you hear the definition and you read the limitations, that is the flow field has to be inviscid, flow field has to be steady, flow field has to be irrotational. There are some of these requirements, incompressible. When we derive these things, you do not have to remember them anymore during the derivation. So, whenever you have to apply this equation, think of the derivation that was done, and while we do the derivation, there are some assumptions that we will make sure that when you are applying it to a problem, the problem, those assumptions that you had for the successful application of Bernoulli's theorem holds for that particular problem. If not, then relax some restrictions, make some assumptions. So, we will talk about Bernoulli's theorem that connects velocity with pressure in incompressible flows. But right now, so we see that drag will have skin friction drag, pressure drag due to flow separation, wave drag due to shock wave activity, and this very important component called induced drag. Induced drag, sometimes it is also known as lift induced drag. Lift induced drag. So, we will try to, so these are the drag components on the wing, and of course, on other components, as I said, some of these will be relevant. So, once you understand these things in the context of the wing, you will figure out if these are relevant for the fuselage or which one is relevant, which one is not relevant. Now, this lift induced drag, induced drag, wave drag, we will talk about this in the context of the wing. Okay, so this one again is just another image of the same thing, a force diagram on the aircraft, where we are showing straight and level flight. It is just because students sometimes have some confusion, because see, this is not a straight and level flight. Okay, there is a flight path angle. On the other hand, here flight path angle is 0. Your V infinity is aligned with the horizontal, and your lift L, reaction force R, drag D, weight W, and thrust T are such oriented that lift is equal to weight, thrust is equal to drag. So, this is the force balance for straight and level flight. So, when aircrafts are cruising at altitude, this is what it is, and there are no moments. So, aircraft is trimmed. So, of course, there are moments, but the moments cancel each other out, so that if you take an axis into the plane of the paper through the center of gravity, the pitching moments are 0. If you take an axis from, so essentially if you take various axes through the center of gravity, you can think of a right hand coordinate system, and you are trying to measure the moments. Of course, there are forces all over the aircraft. So, there are moments that are being generated because of these distributed forces, but they are all cancelling each other out in this special situation, which is the straight and level flight. In fact, the moments on the aircraft are applied when some attitude change, some bank and all these things are required. In most cases, it is really a balance of these forces. Now, that you have the big picture of the vehicle forces that are acting on it, we will now look at the wing, because I said that when you try to understand the drag or the nature of this drag force, you can focus on one of these components, and that wing is one of the most crucial components, because it is the main component that is responsible for generating almost 80 to 90% of the lift of the vehicle. Okay. So, we will look at drag in the context of the wing, and you can figure out drag on other components once you understand the basics of how to calculate drag. So, here you see that we have a airfoil cross section. What is an airfoil cross section? Essentially, if you think of a fuselage, you have a wing going from the root to the tip. What you do is you take a cross section of the wing at some distance from the root chord or the fuselage axis, and that will give you a shape which looks something like this, and that is known as the airfoil shape that the wing is using at that location. Now, some wings might have the same airfoil cross section at every location. Some wings may use different airfoils at different locations. These airfoils might be twisted with respect to one another. We talked a little bit about geometric twist and aerodynamic twist. But right now we are focusing on one particular cross section of the wing. And at this point, I should also draw your attention to something which is known as the difference between a infinite wing and a finite wing. Okay, so for a lot of the theoretical discussions that we have, we talk about infinite wing. And what does infinite wing mean is, so of course finite wing, you understand the wing on an aircraft has a finite span. What is span? Span is the distance from tip of one wing all the way to the fuselage axis and then all the way to the tip of the other wing. Okay, so that is your span of the wing. So for wings on real aircrafts, we have a fixed span, which means that the wing is finite. So it has fixed span and we say that the wing is finite. On the other hand, and in fact you will see that this finiteness of the wing with low pressure on the upper side, high pressure on the lower side, you understand that is the basis of lift. So if you have to keep the aircraft afloat, in some sense you have to fight gravity, you have to have a way in which the force on the lower surface of the wing on the average is greater than the force on the upper surface of the wings. That is what is going to give you a component of force that is fighting the gravity that is trying to bring the aircraft down. Now when you have a finite wing with high pressure on the lower side, low pressure on the upper side, you have flow that will leak across the tips from the lower to the upper side. Okay. So if I draw it here, in case of a finite wing, so suppose this is the fuselage from the front, this is one wing, and I said that on the average the force on the lower side is much higher than the force on the upper side on the average. Okay, from location to location things might vary. So because that is really what provides the net force that keeps the aircraft afloat against gravity. What happens is, force high really means that the pressure on the lower surface is higher than the pressure on the upper surface, because this force is really like the pressure multiplied by the surface area, that gives you the local force normal to that surface area. So if I say that the force from the lower side is bigger than the force from the upper side, it essentially means that the pressure on the lower side is more than the pressure on the upper side. So when this situation arises, flow will leak from the lower surface to the upper surface like that. Okay, so and this movement of flow from lower to upper surface will create something known as the trailing vortices, and these trailing vortices will induce some flow field around the wing and all over the aircraft, because of which you will have that extra component of drag that we said induced drag. Okay, so induced drag is a phenomena that will happen on finite wings, because finite wings have high pressure on the lower side, low pressure on the upper side. Now when I say high pressure on the lower side, lower pressure on the upper side, you have to understand that it's like I'm thinking of like say straight and level flight. In a maneuver, if a aircraft sometimes even flying upside down, things are, you have to understand that in context. So in say straight and level flight, pressure on the lower side is more than pressure on the upper side, and around the tips, since there is no more barrier, you can have flow moving from the lower to the upper side, and that creates this vortex motion that trails from the wing to very large distances. Okay, those vortices that are shed from the wing tips create this extra kind of drag, which is known as the lift induced drag, and you will see that is a very important component of drag when it comes to the real applications, because real applications will always have finite wings, and finite wings will have a termination. Around the termination, flow from the high pressure lower side will try to move to the low pressure upper side. In the process, some vertical motion of air mass will happen that will be shed from the two trailing edges of the wing. Of course, you will see later that it's not just like from the trailing edges of the wing, vortices are shed along the span of the wing. So instead of two vortex lines, essentially you have a vortex sheet that is being shed, but it can be shown that this sheet eventually gets sucked into, not sucked, I mean it gets rolled into the two vortex contrails that follow from the wing tips. But near the wing you actually have a series of vortex tubes that are being continuously shed along the span of the wing. However, when you go to the at a certain distance downstream of the wing, you will see that all these vortex tubes are getting rolled into the contrails. So, these large two trailing edge vortices only, and that we will see that will create this extra component of lift known as the lift induced drag. So, when I say that these finite wing will create this lift induced drag, I am implying that this infinite wing, of course we have not talked about what is infinite wing, that this infinite wing will not have these lift induced drag. So, why is that the case? Easy answer is your infinite wing does not have a wing tip. So, there is no chance for the flow to leak from the lower surface to the upper surface, okay, because you are trying to find where that vortex thing is going to happen, but there is no wing termination. So, there is no way for the lower side to go flow from the lower to the upper. So, there is no this trailing edge vortices. So, there is no lift induced drag, because we said that lift induced drag somehow stems from those vortices that are shed from the finite wing. Now, if you want to measure properties of a infinite wing, are you going to build a wind tunnel that is infinitely wide? What is done is, as long as you take say a rectangular wing of a fixed cross section. So, infinite wing, every cross section should be same as each other. You cannot change the cross section of, I mean you cannot have different airfoils at different stations, because then that will no longer be infinite in some sense, because when you talk about infinite wing, you mean that you do not know where this wing is starting on the left, you do not know where it is ending on the right, and anywhere you are taking a slice. So, all these discussions stem from the fact about the slice. So, this slice, the slice of the wing that we are looking at, you can take a slice on a finite wing and that will show you a flow field, or you can take a slice from an infinite wing. The interesting thing about the infinite wing is, whatever you see in one slice will be exactly same as whatever you will see in another slice, in terms of the airfoil shape, airfoil geometry, size, etc., and the flow field around that airfoil. Okay, for a infinite wing, wherever you take a cut, you will see the exact same thing. So, if I give you 10 different cuts, you will not be able to say which cut is from which location. Okay, that is the infinite wing concept. And if you want to compare that to a finite wing, in a finite wing, if I take cuts from different portions, first of all you might be able to identify just by the geometry if the wing is twisted geometrically or aerodynamically, or if the size of the chord is changing. You can just, without any flow field, you can say that it is a finite wing. On the other hand, suppose you have the exact same cross section, but the flow field will change from location to location on a finite wing in flight. Of course, if it is standing on the ground and you do not have any flow around the wing, then you may not be able to say which section is from where if all the sections are similar. But if in flight, because of these trailing edge vortices at the tip, some distribution is created at various locations on the span that will help you identify that this is from this location on the span, that is from that location on the span, etc. So, now we have, let us focus on this image here, and all we are saying is, let us say that this is the flow field around the wing at this point in time. So, you see that we have, this is known as a stagnation point. Flow is going on the upper surface, flow is going on the lower surface, and as I said that this flow field will create two kinds of forces. So, the relative motion of air around the wing will create two primary kinds of forces. So, forces, one is, we will say, the normal forces. Okay, and that arises from the pressure of the air that is in that location of the wing. So, as your air is flowing, it still has some static pressure because of the molecular bombardment, so collisions with each other. And when these molecules are also colliding on the wing surface, they are imparting some momentum exchange is happening, and that leads to this normal force. So, you see that we have marked it as Fn. So, normal force due to the flow of air over this wing. Secondly, we have this thing called the tangential force. Okay, so tangential force, also known as shear force. Sometimes you will hear the term stress. Instead of shear force, normal force, people will say normal stress or shear stress. Essentially, stress is force per area. So, if you divide the force by the area on which it is acting, you will get stress. So, here as air is flowing past the wing, it is imparting, the wing is seeing the static pressure of air around it, and when you multiply the static pressure by the area on which it is acting, you get the local normal forces. Okay, so, find the static pressure on those discs, multiply it by the disc area, you will get the normal force on that disc. And of course, you get a distribution such as this. And why are we getting a distribution such as this? Why is pressure, you see in that diagram, it almost looks like pressure on the top surface is lower than pressure on the bottom surface. Also, you see that pressure in this region, so the length of these arrows are proportional to the pressure, rather they are proportional to the force that is acting on those locations. And you can see that there is a distribution of, pressure and force are more or less interrelated here, because you just multiply it by the local same amount of area, because the directions are taken care of in the image itself. We are not resolving it in any particular direction. So, the vertical lengths can also represent the pressure magnitudes. So, you see that the pressure is changing all over the airfoils. So, what you do is, if you think this is a stagnation point is nothing but where the flow velocity becomes 0. Okay. So, on the wing, we will see that when we talk about the lift theory of lift, this concept of stagnation point will become very clear. But at this point, okay, is in the subsequent slides we will have some a way to understand this. So, this location where u becomes 0. So, the net velocity. So, locations, there are some locations where v will become 0, that is u comma v comma w. Okay. So, points like those will be called stagnation point. Stagnation points will have the highest amount of pressure. So, you see here the length of this line is the longest. Now, something is happening that is changing the distribution of pressure across the wing. We also see, of course, pressure is decreasing in this region, then pressure is so see up to this point it looks like pressure is decreasing. In this region it looks like, okay, it is not like pressure is decreasing, we have to specify the direction. Okay. So, you see that highest pressure seems like something is happening that is decreasing the length of these arrows, right. So, something is happening, that is the flow is moving and the pressure is decreasing. So, flow is seeing a decrease in pressure. So, we say that in the direction of the flow, or rather because pressure is also dependent on other variables. So, let us use a partial differential notation. So, in this region so pressure is decreasing as S is increasing. Okay. And what is S? S is nothing but like a geometry fitted coordinate starting from the stagnation point, and you can think of it as like starting from the stagnation point. So, if you look closely, this is S. Okay. So, starting from the stagnation point, so something like this. So, if you have if this is your stagnation point, then you can think of a coordinate like this, okay, body surface fitted coordinate, you can think of it, and here your dP ds is negative. So, you will hear the term favorable pressure gradient, that is, as the flow is moving, pressure is decreasing. It's called favorable pressure gradient, and we will explain why it is called favorable pressure gradient. In this region, you see that the pressure again is increasing. Okay, so, this region from here all the way like this, dP ds is positive, and it is called favorable unfavorable pressure gradient, and you will see why it is called unfavorable pressure gradient. But the point of the matter at this point is there is a pressure distribution. So, when flow goes around a wing, pressure is not the same at every point. There is a distribution of pressure, and on the average pressure on the top surface is lower than pressure on the bottom surface. That gives you force on the lower surface greater than force on the upper surface. Hence, the resultant force has a component which is directed in the upward direction, if you are thinking of like a normal flight condition. So, that is your normal forces. The effect of favorable pressure gradient, unfavorable pressure gradient will become evident when we talk about pressure drag due to flow separation. At this point, this is just something to know, that when the flow goes over a body, sometimes it sees favorable pressure gradient, sometimes it sees unfavorable pressure gradient. Even this happens in internal flow fields, say flow inside a wind tunnel, flow through an engine cross section, flow through the diffuser of an engine or the nozzle of an engine. Flow can actually see increasing pressure as it is moving, flow can see decreasing pressure as it is moving, and there are very important implications of what happens when flow sees either of these two situations. Nonetheless, we see that when flow moves over a body, we get normal force distribution. Again, we get this thing called the shear force distribution. What is shear force? Shear force is a force that stems from viscosity, and it acts tangential to the local surface direction. You see that at each of these points, this is the direction of the shear force. At this point, this is the direction of the shear force. At this point, this is the direction of the shear force. So, when you add all these forces and you take a component in the direction of your relative wind, you can see that these things will have a significant contribution in the direction of the relative wind, because you can already see that these forces are almost aligned with the relative wind direction because of they being tangential to the wing and the wing being aligned mostly with the the wind direction. Of course, the angle of attack is there. I am not saying these will exactly align with the relative wind direction, but it's almost aligned with the relative wind direction. So, shear forces arising from viscosity will contribute to drag, and that drag is known as skin friction drag. So, the drag due to these forces really become the skin friction drag. Now, the pressure drag, do not think that just taking the component of these in the drag direction is the pressure drag. I mean, to some extent that is the case, but the real contribution of pressure drag shows up when there is flow separation, and we will see that this unfavorable pressure gradient has something to do with that flow separation. So, we will look at pressure distribution around the wing when that dP by ds positive has created flow separation, and then we will see that the pressure distribution with flow separation creates a significant contribution to the drag force. Here again it's the, so if you have the flow around the airfoil, you have a resultant force arising from the distribution of the normal force and the shear force, and then you can resolve it as lift and drag, okay, lift and drag. So, by now you know that lift is normal to the relative wind. In this case, my relative wind is like this, hence my lift is normal to the relative wind. There is also a way in which you can resolve these forces along the normal to the chord. So, you see this n is the component of r normal to the chord, and a is along the chord. So, it is really dependent on what you are trying to achieve. In some cases, in most cases, we would be concerned with lift and drag. So, we resolve r into forces normal to V infinity and parallel to V infinity, but in some cases you might need to resolve it normal to the chord and along the chord, and of course, there is a connection between them because the angle between these two lines is same as the angle of attack. Now, the flow field around an airfoil is quite complex, and it has a lot of interesting phenomena that is happening. So, although you are seeing perhaps a distribution of pressure like this in the steady state, but to reach to that distribution of pressure, you have a lot of things going on which are of fundamental importance in aerodynamics. So, we will continue with this portion in the next lecture, but at this point I want to just bring to your attention that if you think of an inviscid flow field where you have put an airfoil and you switch on an airflow, you will see that the flow would look something like this. And this is a very strange thing that you will see, that in most cases, unless you align the flow in such a way that you have this phenomena at the trailing edge, in all other cases you will see that there is this way in which the flow is leaving the airfoil cross section. And what is happening here is you see that this flow line has to undergo this very sharp bend along the trailing edge, and this is something that nature is not fond of, or there is some problem in terms of the viscous stresses, the acceleration of the fluid that it has to undergo while negotiating that curve of 0 radius of curvature. So, some of those issues arise, and it is seen that if you run an experiment and you visualize it, you will never see a flow field like this. You will always see something like this. Okay, you will never see the flow leaving abruptly from the top surface or the bottom surface. Flow always leaves from the trailing surface. Okay, this is something which is known as the Kutta condition. It is known as the Now, all these things are important for understanding drag, okay, but all these things are also important for the entire aerodynamics discussion. So, you will see that as we bring this thing into the discussion of drag, slowly and slowly you will see that when we learn this thing on a more generic level, you already have a physical feel of what this thing is and what is its importance. So, as I said that if you have a inviscid flow, or rather I should say a flow that has no viscosity. Okay. See, inviscid and viscid flow fields are not same as a flow of a fluid which does not have viscosity. So, we will talk about these things. Okay. If a fluid has no viscosity, we call it an ideal fluid, fluid with no viscosity. Viscosity is something that creates that friction effect. As the flow goes over the object, it creates a tugging effect. It tries to pull the object in its direction of motion. But a ideal fluid which does not exist will have zero viscosity, hence it will not tug along the surface at all. Real fluids can behave. So, real fluids with viscosity can exhibit inviscid behavior. So, as if there is no viscosity under certain conditions. Okay. It is not that because of they do not have viscosity, they have viscosity, but for viscous effects to manifest, you need something more than just viscosity. Okay. You need velocity gradients. So, if in a certain flow region you do not have velocity gradients, or if your inertia force term. So, this is I should not talk about this thing so ahead of time, but you will see that there are other situations also where a flow can behave in an inviscid manner even though it has viscosity. So, we will talk about these things in the next class, and thank you for your attention. We will continue with it in the next lecture. Thank you.